meeting.
Okay, so I'm Holly and this is Lisa and Marie, and our presentation is on the mathematics of origami.
Wait, it's not clicking. Why is it not going?
Oh, there it
There
goes.
it is.
Okay, so some of the topics we're going to discuss in our presentation is a brief history of origami, some lessons and standards for middle school and high school students, the mathematics behind origami, technology and origami, and GeoGebra and origami. So a little bit of history about origami. The original origins are unknown, but it's assumed to have originated in China because that's where paper was first invented in the 1st century AD. And then paper was brought to Japan by Buddhist monks during the 6th century AD. The oldest documents written were Senbazaru Orikita, which translates to 1,000 origami cranes, and those were written in 1797. The inventor of paper was Kai Lun in 105 AD. And the oldest example of the use of paper folding is the wan boa, which is folded like golden nuggets and burnt as an offering to the deceased. By the 6th century, paper was introduced into Korea and later in Japan by Buddhist monks. Paper was very expensive and rarely available to the general public. The first book published about paper folding was the Tsutsumi no Ki by Sadaki Ice in 1764, which contained instructions to fold 13 ceremonial folds, such as the Noshi and Tsutsumi. And here's a link that will give some more information about origami and special shapes if you're interested. The mathematics of origami that we're going to cover. Oh, go ahead.
Hold on. My apologies. Okay, go ahead, Holly. I apologize. Go ahead.
That's okay. The mathematics of origami that we're going to cover are the hen, the boat, the Pythagorean theorem, and many 3D figures and their volume, surface area, and more. So I'm going to start with some lessons and standards. Origami constructions can be used in math class beginning as young as middle school and then all throughout school after that. Lessons and topics will, of course, increase in the level of difficulty as students get older. And some sample lessons that I'm going to discuss are the hen constructions in middle school and high school geometry and the boat construction in middle and high school geometry. So an example of a lesson that would use the hen construction in middle school in 8th grade could be the standard where they apply the Pythagorean theorem to solve mathematical and real world problems involving unknown side lengths and right triangles. Some of the materials that they would need are a computer or laptop, pencils, rulers, paper that is already in a perfect square to use for constructing the hen, and then have multiple sizes available so that all students have different sizes, and then scrap paper for students to show their work for the math. So the lesson could go as follows. They can watch a video tutorial. If you click the link, it will go to a YouTube video showing the students how to construct the hen, and they can follow the video to do so. And then they can choose 3 triangles in their construction, bisect the triangle in a way that will create right triangles, measure the 2 side lengths of their choice with a ruler, record the measurements, and then they can trade their construction with a partner and use the Pythagorean theorem to find the missing side lengths of their partner's triangles. In high school, it would be very similar, so the same materials needed, but the standard that these students would follow, as an example, could be extend previous understanding of scaled drawings and scale factors to determine how dilations affect the area of 2-dimensional figures and the surface area or volume of 3-dimensional figures. So again, the first 2 steps, they can watch the same video tutorial to construct the hen, except this time each student would construct 2 different ones using 2 different sizes of paper. They can use a ruler to measure the side lengths on the bigger hen that they construct, Find the surface area of the complex figure, that is the hen, using the measurements they recorded. And then do the same procedure for the smaller hen and determine the ratio between the two figures and explain how the dilations affected the surface area of the hen.
Hold on, I'm sorry, technical difficulties again.
That's okay. Oh, go back
Back
one
one.
slide. Yeah. Perfect.
Okay.
So for the boat construction in middle school, I included two standards, one for 6th grade and one for 7th grade, because these two are both very similar. So I feel it could be used in either. For 6th grade, it would be solve mathematical and real world problems involving the area of quadrilaterals and composite figures by decomposing them into triangles or rectangles. And then for 7th grade, very similarly, solve mathematical or real world problems involving the area of polygons or composite figures by decomposing them into triangles or quadrilaterals. Similarly to the last lesson, they would need a computer or a laptop, pencils, rulers, perfect square pieces of paper again in multiple sizes, and scrap paper for their math work. For this construction, I included another video tutorial that will lead to a YouTube video that the students can watch to construct the boat. And in this middle school lesson, they would use a ruler to measure the side lengths of their construction and then use formulas to determine the area of each individual triangle and quadrilateral in their construction, and then determine the area of the whole boat by using their knowledge of area of composite figures. And then for this lesson extended into high school, the standard would be to prove relationships and theorems about triangles and solve mathematical and real world problems involving postulates, relationships, and theorems of triangles. The same materials needed as the middle school lesson. So again, they could watch the same video to construct. And again, for high school, they would construct it 2 different times using 2 different sizes of paper. They will measure 2 side lengths of each triangle using a ruler, and then using their knowledge of triangles. Sorry, there's something going on outside. Using their knowledge of triangles, determine and prove all possible side lengths of the missing side of each triangle. As an example, they could use the Pythagorean theorem.
So I have to go forward and then back because of the recording.
No worries.
Marie, you're
so
on.
this is how the hen would tie into special products. So when we do FOIL, we know that a minus b squared, for example, where does it originate from? A lot of students have trouble conceptualizing what the middle part of that formula goes or how it's derived. And so this little square in the pink is the origami fold, and it shows you basically how we're subtracting areas. So if you look at APSO as an area, that's the value of the A. And on this side, we have the B values. So this would be the B squared part of that fold. The other side, the SORD portion, this is the A minus B squared. And the rectangular area here, OQRC, comes to B times A minus B. You'll notice in the formula, we have an A squared. So A squared is one of the areas. A minus B times B and minus B squared, which is this OQRC, minus A minus B times B, which simplifies, believe it or not, into the fold of A squared minus twice AB plus B squared. And I too share a link here for how to understand the connections between the fold and once you unfold the hen, what it looks like and how you calculate the FOIL. Kind of looking at it in terms of areas going back, the area SORD basically is equal to the area of ABCD minus the area of APOS minus the area of PBQO minus the area of OQCR. And that's in essence what the formula shows. A little bit more complicated than the boat, which is the next slide. The boat is the A plus B squared. And so as a product, this is a squared plus twice ab plus b squared. A little bit easier to understand because when you unfold the boat, it looks simple. It's just area 1 is the a squared, area 2 is the b squared, and areas 3 and 4 are the a times b, hence twice ab. And so once again, there's a link. You can watch it. You can see how they correlate the fold and they unfold the paper, and you'll see the areas calculated. So if we go forward to the next one, this is basically Pythagorean theorem. It's a pretty boring fold. I found it to be very boring. The center square obviously is c times c, so the area is c squared, but you'll find that as you fold these, you end up with a squared plus b squared, where a is the shorter sides, b is the longer sides here. And once again, you can see this link, which will also enhance a little bit or further elaborate on this. Next. So I'm going to start having a conversation because what I really want to show you is coming up in the next few slides. But this is a simple pentagon, and we often have lessons talking about the apothem length, which unfortunately students tend to forget by the time they get to our high school or even college level. And so this is a simple one-dimensional area of a pentagon, how we calculate it using the apothem and the side length. In the next few slides, this is what I'm really excited to share with you. So in this slide, I have buttons which you can click on once you get the PowerPoint. And for example, if you click on the tetrahedron, you'll notice that it will take you to GeoGebra. Give it 1 second. And the beauty of this, once we get this opened up, you can see that there is a tetrahedron, a prism, three-dimensional prism right here, which we can actually make it disappear. So if you go to the left side of the screen, you should be able to see where you have the slider.
It's on the
Yeah,
algebra,
so
right?
go over here, scroll up a little bit, and you should be able to see the tetrahedron and the slider, but it needs to be, yeah, there you go. Down here, where it says F tetrahedron, it's pink. Yeah, go ahead and click on the little button. You'll see that I'm actually going to make the tetrahedron disappear. So just click on the pink button.
The pink button.
Pink button, yeah. You see how it disappears. So the way I would use this and have used this is basically have the student draw a perfect equilateral triangle, measure it out with paper and pencil, and make sure that the angle measures are each perfectly situated. With the center triangle, the center triangle, which is in the beige, you'll see the red, the yellow, and blue, which are also perfect equilateral triangles. And so you can consider this to be the equivalent of your origami paper. So this is a basic construction, and we can start by measuring the sides and making sure that each side is the same. We also would take angle measurements, just as I did here. You can tell that each of these angles will be 60 degrees. And I also attached the different formulas, and what you can do as a student from a teacher perspective is be able to tell different measures and how they relate. What's really interesting though, if you would also take the slider and move it towards the zero slowly, you'll see that you can actually model how the origami paper should fold and have student actually use that as a visual. It's a great visual. The other element I wanted to show you, or the other figure, which is common, and it's taught, and I'm so glad Holly went into the specifics of the standards, because in the SAT, the standardized test, it is, and also the ACT, they need to be really proficient at understanding what happens to volume, area, the different measures, like what is good for a two-dimensional figure versus a three-dimensional figure, and they need to understand how it affects area, how it affects volume, how it affects, different measures. The next part of my presentation is what I'm really excited to share with you, and that is the use of GeoGebra to create origami cutouts, to create tetrahedrons or rectangular prisms, pentagons, hexagons, heptagons, octagons, whatever you wish to create. I would also like to share with you how I created this, because I think it will be a help for you as a teacher. So I'm going to start with the first figure. So we're going to start with the tetrahedron. I think this is probably my favorite at this moment. What I love about the tetrahedron, as used here, you can actually demonstrate the various measures of the edges of the equilateral triangles. You can also verify the angle measures of the equilateral triangle. As you can see here, I'm moving the 60 around for this particular angle. So with a compass straight edge, simple paper pencil, they can actually create the origami cutout of an equilateral triangle. And while they're practicing the measures, if you use colorful paper or give them some way to color it in, it'll be fun for them as well. If you notice also, I hid the tetrahedron, but I'll bring it back and then show you what it looks like. So they do have tetrahedron like Rubik's Cube or Rubik's related diagrams and figures. There are some three-dimensional figures we can use in teaching that will reflect this figure. And you can also show the student that if you were, for example, wrapping it, you can bring it up as such to the point at the very top tip, and you can perfectly wrap that figure. And that is the idea as they're creating this three-dimensional tetrahedron. As you discuss the material with them, you can go through the calculations of each edge, the area of each edge. For example, I could take the area of each of these triangles and practice that. That right there would be 4 calculations of area, which is good. As you wrap this up, you can also talk about the correlation between the formulas, a surface area, and a volume, which are all interesting calculations. Now, why this is important is these calculations are often tested in standardized testing down the road. So it's good practice to get them really comfortable with these measures and calculations. I'm really excited about showing you how I did this. So let me show you a live demonstration here. So let's do a new one. And we're going to do a simple, let's go to regular polygon, and I'm going to select this and this. If you notice, all I did was select 2 points, and now the number of vertices. So let's say hypothetically I want to do, let's do an octagon. All right, so that's an 8-sided figure. There you go. There's your octagon. Once you do that, go to this value here and go to extrude prism. And once you do that, click on the actual prism, and then it's asking you for the altitude. Now, for the sake of the example, I'm going to do a simple altitude of like 3, which is enough for the diagram. There you are. And then once you have the altitude, go back to that tool here, and we're going to select net and click on the figure itself. If you notice, the brown area down here is your actual origami paper. If I take the prism and I make it disappear, that's what the students are going to end up cutting out on the paper. Notice that there's the bottom down here and there's the top up here. And so they're going to have to not only make the octagon base, but they're also going to have to make sure that they measure out the top, which is very easily done if they fold it. All right, so if this is the beauty of it, you can now demonstrate why you need to make sure that you have the top attached. What's also interesting here, and one of the elements that I love about this, is the angle measure. Remember, you have to figure out how many degrees we're going to measure in this particular region here as I cut out the paper. So right here, you can see that's 45 degrees. So I'm going to move this so you can see it carefully. And all of these cutouts here are going to be 45 degrees, every single one. You also need the interior measures of the angle, which is important because they have to know the formula side minus 2 times 180, which gives you the grand total here. So for example, in this case, that divided by the number of sides, which in this case is 8. That's the wrong point, sorry. Let me clean that up 1 second. Hold on. I clicked on the wrong angle measure. All right, so let's go back to angle measures. And I want to select, let's see here, which is the most clear, this one. So from here, I want angle E. And you see clearly here, angle E is demonstrated. Let me bring it forward. You can see that angle has to be 135. And that means all of these angles have to be 135. And we get that from the formula, side minus 2 times 180, and then that value divided by 8 gives us 135. All right, and then also the edges is important. We want to do the edges, so the length or the distance of each edge, they all have to be the same. So if you notice, this one is 3 and 3. If you can't see the 3, I'll move it so you can see it. Right there. And I'll give you another measure. Let's do the edges. I don't want an angle, I want an edge. There you are. And so I caution you not to use decimals. Try to use values that are solid, like 4 or 5. No decimals. Try to stay away from it. Just from experience teaching this, it makes it a little tougher to measure out. I mean, depending on the quality of student you have, how much detail you want to put into it. Now, what's another interesting area aspect here is the area. We could talk about the area of this particular segment or this one. If you notice, I'm clicking on all of the sides. Okay, so each of these should have the same area because they have the same edges, and you can discuss that as a point of discussion. If I want the area of the top of the octagon, there you are, which should match the bottom of the octagon. There you go. And so you can discuss this with them. I can click it twice. I want to be able to see it a little better. Let me see if I can move this one just a tad. But lots of ideas, lots of ways you can use these this tool in terms of having kids explore and understand how to use the paper creation of origami paper and construction. So let me show you my pentagon. Let me go to open. So this is one I actually already did. We're not going to save this, unfortunately. And there's my figure. And let me see where, here we go. Here's my, where's my prism? There it is. Boom. So 5-sided prism. And if I go ahead and I want to wrap it, there you go. I'm wrapping it. And it's a cute little diagram. Really fun for the holidays, I think. I typically have my students cut this out. If you think about it, they're doing all the measurements. They have to use paper, compass, straight edge. And their job is to put a note inside once they close it up and give it to someone as a gift. It has to be a nice note. So make sure we check that out. So yes, this particular lesson is quite fun to do. In this particular example, notice that I also have 5 minus 2 as in 5 sides. Minus 2 times 180 is 540 degrees. And then 540 degrees divided by 5 is 108. And thus each angle between the folds is 72. So this has to be 72 here, here, here. And inside of here, let me erase the prism for a minute. you'll notice that all of these angles are 108. Okay? You also do the sides, the edges once again. And even so, I also discussed the apothem. The apothem is right here. You can see it at 2.08 as we find the area for just the pentagon. So you can have fun with this and learn quite a bit. Have the kids explore and just have fun with it. So let me see here. Yeah. So area here, 15.78. Close enough. Must be a rounding issue. But yeah, area of the pentagon. These are the pentagons themselves. Fun activity for the holidays. Like I said, I have them cut this out, and the net is like your origami paper, and demonstrated. You can actually fold it, like I said, and I always tell them, put a note inside of it. It's pretty paper, pretty diagram. Give it to somebody as a gift. Why not? You can also talk about surface area, which is 5 sides times length times width plus width times height, which in our case comes to 121. You can also do the volume, and in this case the volume comes to 114. So have fun with it and have them explore and do all sorts of calculations, and it's a great activity. So if you will click on rectangular prism for me. And so here's the typical cube, and they always ask questions about the cube. What I like about this one is this is especially for the holidays. I cannot explain how entertaining this can be. We are looking at the paper. This would be the equivalent of your origami paper, which you have to shape yourself. So you give them a typical rectangular piece of paper, and they have to measure out each of the angles, each of the rectangle sides, based on the criteria that you hold them to accountable for. And if you click on the prism right above the gray button,
Here,
there's your
B.
prism. Yep, click on that and you'll see that is your prism. So the net that we use is like our origami paper. And so if you click on the 1 and the 0, bring that 1 towards the 0,
Oh,
you'll
sorry, let me go
see
slower.
how it folds. And so there's the bottom, there's the figure, and that's what it should look like once closed. After that, they can take the area of each of the dimensions, whether you want the area of each side or the tops and bottoms. You can do the volume once it's closed, a closed figure. There's lots of different applications for this. I also did the pentagon. That was also fun. And obviously I'm going to stop at pentagon because I think that's, you know, I went a little overboard, but this is, again, I love doing this one with them because there are a lot of measurements they have to take. They have to take the interior angles, which one of the formulas they need to know for SAT is side minus 2 times 180. They have to know the interior angles, the exterior angles as well. They have to discuss why 1 is 72 and 1 is 108 on the inside versus the outside. And again, there's your apothem showing up again. And so all of this calculations that include surface area, volume, we have the area of a single pentagon, or just a flat one dimension, apothem length. So all of these calculations you can expect from them. And between, you know, having to take a piece of paper and actually obtain that net diagram that we use in our origami to fold and eventually create our prism, it takes a lot of work. So I would also suggest not to use values that are decimal based. I did this on purpose because I'm teaching it. So it's a little different. If you click on the prism, Lisa, you notice the prism is sitting right there. So it's like folding something, right? If you were folding a gift. And what I always tell them is once we fold the paper, put a little note inside of it and give it to a friend,
Oh,
making
cool.
a nice note for like the holiday. Why not? So lots of math that you can use here. I was so excited to show you guys this. And I'm not going to do the hexagon, a heptagon, an octagon. I even did a nonagon, but I stopped.
Marie, did you already have these done for your SAT prep classes, or is this something that you made specifically for this presentation?
Once I did this class and I started exploring this, I actually threw this into my SAT prep and my students were blown away. Love
Very
it.
cool.
Absolutely love it.
All right,
So what's next?
I think I'm next.
I think you're next.
I mixed up some of the slides, so my apologies. So I'm going to be showing the use of GeoGebra, not 3D, 3D and 2D figures. I do want to show a link, an outside link that is not our own, that we did not do, that has a ton of amazing 3-dimensional and 2-dimensional examples of origami on GeoGebra. So these were kind of my inspiration on making my own GeoGebra animations of the hen in the boat, but I could not get it as complex as this. So the link is in the PowerPoint. Feel free to share, go in and play around. And I don't know what just happened. Give me a second. But I'm going to show what I did do. So we'll start with the hem here. So I took the video that Marie shared, and first I folded it with paper just so I can kind of get the hang of how it was folded. And then I took it and put it onto GeoGebra. Now, figuring out how to fold a paper on GeoGebra is not an easy thing to do. So it was a lot of research on Google, and I've seen examples. It's not something that's done, which is surprising to me because it's something that's actually kind of cool, and it's a really cool animation that you can do. So in our research, in the resource section, there are some links of different resources that we used, or that I used to basically get the hang of this. But what I really started thinking about is the points of the paper. So if for the first step in moving the hen, you fold from the top left to the bottom right. And so the way I thought about it and to model in GeoGebra is to take the point, not the specific point that's up here, and rotate it down to the bottom to get this fold. And then I drew the shape later. And then the next step, I believe, is to fold up the paper. We'll fold in the tip for the hen's nose, and then finally fold up for the hen's foot. Again, this is only 2-dimensional. I could not figure out how to put this in a 3-dimensional format, but you can see how GeoGebra can be used to model that 2-dimensional hen being folded. And then I'll also show the boat. This is a little simpler to do. This one I put in the fold so you could see, just to show the area that Marie showed earlier. So like she said, you can use this to show the quadratic formula, not the quadratic formula, a squared plus b squared. Correct me, Marie, a squared.
Special product, a plus b squared.
Yeah, thank you. All right, so again, I thought of the corners, folding it from top to bottom, and then folding the top up, and then folding in the section of the boat. Now, ideally, you would flip it and to make it 3-dimensional, to make it float. But again, it could not figure out how to do that in a 3-dimensional way. So we'll just do it 2D for now. And then these are embedded in the PowerPoint. I did do these on GeoGebra and on the GeoGebra website for anyone to play around with. Okay, so some technologies that were inspired from origami that we found in our research are listed here, as well as more videos about technology inspired by origami. Origami is something that has been around for ages. And, you know, you think about it as just like this hobby that people do for fun, but to see like what it can be used for and the math behind it was the really interesting part about completing this particular project. And here's some more as well. It seems like it's used a lot during with space and with robotics.
Mhm.
And this is all references of information that we used in order to complete this presentation. Ladies, any questions or anything we missed?
I don't think so. I did want to show at some point like how I arrived at making the 3D figures. So I guess if anybody wants to learn, they can always send me an email or text and I'll walk you through the steps, or I could show it now. It's up to you guys. Are we doing good on time?
We're 45 minutes we're supposed to have, right?
So we're good?
Yeah.
Are we at 45? Then
No.
yeah. So we're
You have
not
time
at
to
40.
show.
Okay. So then let me go ahead and steal the reins for a minute. I'm gonna share my screen. So let me do that because that would be helpful, right? You'd like to see it. So okay, I need to go to GeoGebra.
This is something that I wish that the creator of those 3D and 2-dimensional
Would have shown.
would have shown. I was looking everywhere for resources of how he
bet.
did it, and I could not find it.
I bet. So yeah, let me take a minute. It won't take too long. I'm trying to get to GeoGebra Classic. Where is my Classic? Oh, let's go there. Okay, fine, whatever. All right, so I just want Classic. Where's my Classic? Do I have to type in Classic?
You can just go from geogebra.org.
.org?
Yeah, and then
Okay.
in the top right, click on the little 3, not the sign in that one. And then you can just go to the geometry.
Oh, gotcha.
Oh, down at the bottom, you see it?
I think I missed it. Hold on. So where am I going?
Back to that, and
Right
then
here,
there you go.
Classic. Got it. Thank you. So, okay, so I'm gonna go to 3D graphics, and what I did was I selected a couple of points. Now I'm freaking out. Let's see. All right, so let's say I choose 2 points, and I'm gonna go to. Do I want a prism? No, I'm gonna go to regular polygon. So let's make something simple. It's gonna ask me for 4 sides. So let's do the cube, I guess that's easy. So 4 sides. I then want to select extrude to prism. And it's asking me basically when I do that for the height. So let's go with a height of 6. So there's my prism. What I do want to do next is I want to actually go back to that link or to that point, and I'm going to select the net. So select net and click on the object, and there's your net, which is the equivalent of our origami cutout. And so now you can see how it folds, and you can change the colors. And like I said, you can choose all sorts of measures. It's I mean, it's a great tool to teach and to also have them explore. So that's how you make it. And you can make
So
any
simple.
size. Yeah, it's very simple. Yep. That's it.
Marie, thank you for sharing.
You're welcome.
Yes, that was really cool.
Now, if they had like a little one that said origami and you clicked on it and it just put it all out there, that'd be great.
That would be awesome.
It's something I'm going to keep exploring, I think, though, to try to figure it out.
I actually have found myself using this stupid little program and just going to town on it. And that's like, I'm a married person. I don't have time for this. You know, I have other things I have to do. But no, going crazy with this stuff. All right, I'm going to stop my share. All right. So that's our presentation.
Stop the record too?
Huh?
Stop the record?
I can. So that's our presentation. Good job, guys.